This is our f of x. So then we want f prime, 1 over 2 the square root of x plus 1 minus 2x plus 1. We have to put this function in the graphing calculator because we need to find an interval where a solution exists. So let's do that. So in y equals, because I don't know, the square root of x plus 1 and then minus x squared plus x. So second in table, I already see 0 is positive. Let's say 1. So let's go back. 0, 1, 2. Okay, so I found between 1 and 2. Which one do you want to pick? Sx0, very good. X0 is 2. So then I go back and in the function I put in, I insert x minus, put parentheses around the top all the way. This is the function. It goes in Newton's method as the top function, the numerator. Close the parenthesis, divide by, in parentheses, by the derivative. You don't have to simplify, just put it in, but be very careful how you put it in. So divided by 2, the square root of x plus 1. Close the parenthesis. 1 over 2, the square root of x plus 1. Yes. Outside, negative 2x plus 1. And close the parenthesis. Are you with me, everyone? Is this okay? Okay. So now we go to second and quit. We go to variables. We go to y variables. We call the function. It's function y1. I plug in 2, close, and enter. And then I continue by copying the previous entry and replacing 2 by the previous answer. Make sure it's simplified, clear. There is no problem there. Press enter and repeat. Press enter. Oh, we did not establish how many digits we want. 6 decimal places. Is that okay? Mm-hmm. So x1 was 1.874436. x2 was this. x3 is this. And we're getting closer. Do I need to copy all these down? So x1, 1.8744365. Make sure you copy 7. Then x2, 1.9040712. And then x3, 1.8952359. 2467. x4, 1.89773939. 2467. I only need 3. And then I repeat. Maybe now it's going to be the same. So I have 1, 2, 3, just 3 digits. So I have to continue. So in this case, the method converges in more steps. That's okay. 7170190. Okay, let's see what happens next. We're getting close. Okay, 1, 2, 3.
I don't see how his number's going up. And then goes down again.
Oh, I have to check. What I would have done normally in this case, I would have gone back and just put in like 1, start at 1. But I'm getting there. It just takes a little while. So now I already have 6 digits. Yes, it may bounce around a little bit, but not at -5 and then +3 and then -3 and then +4. Yeah, it may a little bit, depending. So it converged a little bit more, a larger number of iteration, but it did. So once I see 6 digits, so this is the last one. So it's 1.897179. And I stop. Yes, in certain situations, it takes a little longer. But it converged. Very good. Stephen, is this okay?
Yeah, could you explain the buttons that you use on the calculator again? Just real quick, like how you got to plug in the y into the
Y1 with the parentheses answers, you have the variables.
So I go to variables. After you put, do you have Newton's method they already put in the calculator? So then you go to variables,
Okay.
and then click on, go to the right on functions.
Yeah, wait,
And then it will highlight y1 as first function. And just press enter.
Okay.
So one more time, if I clear everything, so we do this. So do you have Newton's method here already? As x minus f of x over f prime of x?
Yes.
Okay, so then you go second and quit, go to variables, go to the right to y variables, click on function. Are you there? And then click on y1. We decided to start with 2, with parentheses, and press enter, and it gives you this number. And then you copy second and entry. It copies this, but you don't want to plug in 2 again. So go to and overwrite 2 into second and previous answer.
Okay.
And now in y1, this is the number that the calculator will plug in. And press enter. And then second and previous entry, and press enter. And then second and previous entry, and press enter. From that moment on, you don't have to adjust anything, because it will automatically put in y1 the previous number.
Awesome. Thank you so much.
Thank you. Okay, anything else? Anything else? Well, so we decided to have the test 3 on Monday? Okay, so please come in early if you have more questions. Okay, so I'm here, I'm sorry? So I'm here from, my previous class ends at 6:15. So you have 45 minutes if you want to come in early and ask questions. That will be great. Is that okay? Okay. So we are not going to forget about 4.9. This is crucial. But because I don't want you to get confused in any way, shape, or form, I only have half an hour, so it's not a lot that we can accomplish from Chapter 5. But I think you're going to have no difficulties with what I'm going to do today. So Chapter 5, integrals. I'm not going to define them today. I'm just going to give you the preliminaries, the basics, before we even talk about integrals. So let's look at a basic function like, for example, x squared plus 1. It's kind of basic, right? It's a, what? It's a quadratic function, base function x squared, so it goes up 1, right? So let's take a look. I'm going to pick an interval. Well, let's say the interval is 0, 4. And let's suppose the idea or the requirement now is find the area under f of x between 0 and 4. And the x-axis, of course. I'm going to graph this function. 1, 2, 3, 4. So when x is 0, y is 1. When x is 4, y will be 15. 16 plus 1, 17. Okay. So I'm going to take a smaller unit, or I graph it again to show you, or I'm just going to maybe change this into a little bit less. Okay, 2. Good. So when x is 2, 2 squared plus 1 is 4. Okay, 5. 2, 3, 4, 5. When x is 1, we have 2. So this is the graph of x squared plus 1 between 0 and 2. Now, we would like to approximate this area because we can't determine it algebraically exactly, right? So how do I want to approximate? There are 3 possibilities for now, 3 options. Use the rightmost point. I explain what that means. The second option is use the, what do you think? Most point. And of course, the third possibility is use, exactly, use the midpoint. So let's suppose we start by using the rightmost point, and we have to decide how many intervals, subintervals we want. Let's say we want to use for now 2 subintervals with 2 subintervals. If I want to use the rightmost point, and I'm using 2 subintervals, I'm going to say that this is the first rectangle, and this, with the rightmost point, is the second rectangle. It is obvious that using 2 rectangles for this graph and using the rightmost point, the area that I get is an overestimation of the correct area, of the exact area. Would you agree? Because there is a piece here that is not under the graph, and there is another piece here that is not under the graph. So I'm going to write that the area right 2, using the rightmost point with 2 subintervals, is approximately base times height, 1, because that's the width of the base, times height, which is f of 1, plus 1, which is the base of the next rectangle, times f of 2. So I approximated the area under the graph of x squared plus 1 using 2 rectangles, base times height, base being 1 and height being f of 1, and then the other one, base still 1, the width of the second rectangle, and the height f of 2. Would you agree? Mm-hmm. So then we obtained, when x is 1, we get 2, plus f of 2, we get 5. So this is 7. Let's see what we get with 2 subintervals. Left 2. This time, this will be approximately, and let me graph it again here. This is 0, 1, and 2. This is our function x squared plus 1. So now with the leftmost point, I will have still base 1 times the height f of 0 plus still base 1, but times the height f of 1. This is definitely what? an underestimation. Okay, very good. So f of 0 is 1, f of 1 is 2, so the area is 3, with the leftmost point of the interval and 2 subintervals. Now let's take, go ahead.
I'm too tired to think.
So do you want me to repeat this?
Yes.
Okay, very good. Is the first one clear?
Yeah.
So if I use 2 subintervals and I use the height of the rectangle, the rightmost point, then I get the base times the height plus the base times the height.
So you were starting at 2.
I start from 0 to 2. So the interval is 0 to 2.
Yeah.
So I have a rectangle between 0 and 1, and I have a rectangle between 1 and 2. To determine the area of this rectangle with the rightmost point, I say base times height. 1 times f of 1. To determine the area of this rectangle, I say base times height. So 1 times f of 2. So that's how we got 1 times f of 1 plus 1 times f of 2. F of 1 was 2. I don't even multiply by 1. It's 1. So this is f of 2, which is 2. F of 1, which is 2, and f of 2, which is 5. So the area is 7. So far, so good?
Yeah.
Okay, the next one. This time I want to determine the area or approximate the area still with 2 subintervals, but using the leftmost point. Okay, so between 0 and 1, the height now is at 0. Between 1 and 2, the height now is at 1. So this time, this rectangle is base times height, 1 times f of 0, plus 1 times f of 1. F of 0 was 1 times 1 is 1. F of 1 was 2. 2 times 1 is 2. 1 plus 2 is 3. Better?
Yeah.
Okay. So now I want to determine the area with the midpoint 2 subintervals. So I'm going to graph it again. So this is 0. This is 1. This is 2. Here's what happens next. Right in the middle, this is 1 divided by 2, and this is 3 divided by 2. This is the height now, and this is the height now. So this is now the area of the first rectangle, and this is now the area of the second rectangle. So this is approximately base times height, 1 multiplied by f of 1/2, and plus still base times height, which is f of 3/2. Is this better? Okay. So then f of 1/2 is 1/2 squared plus 1 plus 3/2 squared plus 1. Because this is x squared plus 1, x squared plus 1. So we get 1/4 plus 2 plus 9/4. So this is 10/4 plus 2. So 18/4 or 9/2 or 4.5. As expected, 4.5 is in between 3 and 7. Which of these 3 approximations you think is the best approximation? The midpoint. The midpoint. The rightmost point was an overestimation. The leftmost point was an underestimation. The midpoint is the best approximation. So this is the upper bound. This is the lower bound. This is somewhere in between. Okay, so now here's my question. What if I go from 2 subintervals to 4 subintervals? Do you think that I get a better approximation with 2 subintervals? I know it's a silly question. Or the 4 subintervals? 4. Okay. What if I go now to 8?
8.
What if I go now to 16? Right. What if I go now to infinity?
32.
if I go now to infinity?
We're never
We will. Okay, so here it is. So first of all, let's express the area. So the area is approximately the width. This will be the width of any, assuming we divide it up in the same length, the width of any subinterval denoted by delta x. And we'll determine it in a minute. Multiplied by, what did we multiply by?
The height.
Which is f of x. Right? It could have, if we had three options for f of x. Using the rightmost point, using the leftmost point, or using the midpoint. But it's still f of x. In all situations, I had to plug in that particular x value into the function, right? Perfect. So now, let's say this is our subinterval. This is our interval a comma b. And we want to divide this subinterval into how many? We want to divide them into n. N subintervals. This will be, what is the length of each subinterval? Delta x is the length of each subinterval. Can anyone give us? How much should delta x be? If I divvy up the interval between a and b, thank you very much. Very good. So this will be delta x. 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 Delta x, delta x. How many of them? N. Very good. So if this is the initial value, can anyone tell us what will x1 equal to?
A minus delta x.
It will start at x0, right? Or a plus delta x. Or, that's better, a plus 1, I know I don't need that, delta x. Can anyone give us x2?
A plus 2 delta x.
Awesome.
And so on.
And can anyone give us x3?
A plus 3 delta x.
Perfect. Can anyone give us what is called xi?
A plus I delta x.
Awesome. And so on and so forth. And what will xn be?
A plus n x.
Perfect. Perfect. Great. Okay, so we have, for now, we discussed this piece. This piece is very clear. It must be f of x I. So then, the area is approximately b minus a divided by n, which is delta x, multiplied by f of xi.
Is that I in like the imaginary I?
No. Very good question. No.
But I can.
Where I goes from 0 to n. But I'm missing something here. I'm missing something in this piece. So I'm saying the area is delta x times the first xi, so times f of a plus delta x, plus b minus a over n times f of x2 plus b minus a over n times f of x3 plus b minus a over n times f of dot 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 xi plus b minus a times till I get to the n. So I'm missing something here that is called sum. I have to create a sum, right? How many did I have before? Well, I happen to have two subintervals. That's why I only had two. Delta x times f of x1 plus delta x times f of x2. If I had 10 intervals, I would had 1 times f of x1 plus 1 times f of x2 if I'm using the right point, and so on and so forth, 10. So that's why this must be a sum. So the area is approximately the sum of all these areas of each rectangle, right? Base times height when I is 1, plus base times height when I is 2, plus base times height till, and so on and so forth, right? We do not write SUM. We do write a Greek letter, however. So the sum is denoted by the sigma notation, or the Greek letter S, not by the Latin S. And in this case, we have how many subintervals? N, from I being the first subinterval till N of delta x times f of xi. Let's try to understand what this means. When I is 1, I have delta x times f of x1 plus, because the sum says plus. Plus what? Delta x multiplied by f of x2 plus f of x3 plus 3 dots plus
delta x times f of n. Xn.
correct. Perfect. So I know now that the area is approximately the sum from I equals 1 through n from delta x f of xi. And I'm missing one last piece. I want to change this symbol into this symbol. Let's think for a moment. I don't want any approximation. I know I have 2 intervals, subintervals, and then 4, and then 6, and then 8, and then 16, 32. I have n, but it's still not enough to make sure that I covered every tiny little piece. Thank you. Exactly. And now it's guaranteed that this is no longer an approximation symbol. This is guaranteed to be equal. This has a name. It was invented by a mathematician by the name of Riemann. And it's the Riemann sum. So the area, and we're going to write this down, the area under the graph of a function on a closed interval equals the limit of the Riemann sum. That's it. So the area under a graph of a function is, no approximation, is equal to the limit of the Riemann sum. So now a few things that we would like to look at the summation notation or the sigma notation. So this is the sigma or summation notation. Of course, every time we invent a something, it comes with properties, right? Okay, so here are a few properties of the sigma notation. The sum of ai plus bi from I equals 1 through n. Yes, it's the sum of ai from I equals 1 through n. What do you think? Plus the sum of bi from I equals 1 through n. Do you think that this property changes if there is a minus instead of a plus?
No.
No. Here's one more property. The sum of a constant times ai from I equals 1 through n. What do you think? Awesome. Because it's that one, right, that we just, okay, very good. Sum from I equals 1 through n from ai, because this does not depend on the index. So this is called the lower limit. And this is called the, very good, lower limit and upper limit. Very good. So then, just one thing before we continue. When I write the sum from I equals 1 through n from delta x f of xi, can I use any of these two properties? And of course, only one will work.
The second one.
Yes, this does not depend. It's a fixed number, b minus a over n. It does not depend on the index. It's always the same. I can put it in front. And we're going to do that. Now, we can only calculate by hand the limit of the Riemann sum only with polynomial functions up till degree 3. We cannot perform any calculations with to determine the limit of the Riemann sum for a trig function, for a natural log, for an exponential. We are limited. We can only determine, we can find by hand. I'm talking about by hand. We can find the limit of the Riemann sum only for linear, quadratic, and cubic functions, nothing else. Don't even try, in this class anyway. And cubic functions. Okay. Let's take a look at the sum of 1 from I equals 1 through n. What does this mean? It means when I is 1, 1, plus. When I is 2, 1, plus. When I is 3, 1, plus. When I is n, how much is this? Very good, indeed. Okay, the sum of I when I equals 1 through n. So this will be when I is 1, 1, plus when I is 2, 2, when I is 3, plus dot, 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 plus n. Okay, we can prove this using mathematical induction, but this is, and we have to memorize it, sorry about that, n plus 1 divided by 2. If you say, show me, I'll show you a proof. I have 2 more to show you, and then you can choose one, and we can prove it if that's what we want. We used to prove these in pre-calculus, not anymore. I don't know why. So now the sum from I equals 1 through n from I squared. What do you think this equals to?
1,
Plus.
4,
Awesome.
9,
Plus dot dot dot. Perfect. Plus.
n squared.
Good. We have to remember this one too. N plus 1, 2n plus 1 divided by 6. And there's only one more. Of course, if I said linear, quadratic, and cubic, what do you think is next?
Cubic.
Correct. I equals 1 through n, I cubed. What does this mean?
1, 8, 27.
Good. N cubed. This is easier to remember if you remember this one. It's this one squared. We still have a few minutes, 10 minutes. So if you'd like to prove any of these, we can choose one. There is nothing to prove here, obviously. But if you'd like to prove any of these, we can use mathematical induction and prove them.
Squared.
You want to prove this one?
Yeah.
Okay. So the method of mathematical induction has 2 steps. Okay? Very good. Mathematical induction. Yes? So we want to prove that the sum of I squared equals this. Great, thank you. So we want to show that the sum from I equals 1 through n I squared, which is 1 plus 4 plus 9 plus dot 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 plus n squared, is n plus 1 to n plus 1 divided by 6. Ready? Mathematical induction has 2 steps. In step 1, we will denote 2 pieces in step 1. We will denote this by P of n. What am I denoting by P of n? Not this. This. So this is like a proposition, if you want. P of n is 1 plus 4 plus 9 plus dot 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 n squared is n plus 1 to n plus 1 over 6. So after I denote that, I'm going to check when n is 1. Okay, so P1 is when the first term. If I have P2, then I have the first 2 terms. If I have P3, then the first 3 terms. The first term is 1. And I'm checking whether it equals this expression when n is 1. 1 multiplied by 2 multiplied by 3 divided by 6.
1.
It is. So I'll say yes. Now step 2 is this what it's called the induction step. What does that mean? Well, I'm going to say assume that Pn is true. And you can say, what kind of proof is that? You will see in a minute. I assume that Pn is true. Then, based on Pn, I find Pn plus first. What does Pn plus first mean? Means this 1 plus 1. Meaning what? 1 plus 4 plus 9 plus dot 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 plus n squared plus n plus 1 squared equals n plus 1, n plus 1 plus 1, n plus 2, 2n plus 2 plus 1 is 2n plus 3 divided by 6. So what yes, I replaced n by n plus 1. n becomes n plus 1. N becomes n plus 1 will be n plus 2. 2n plus 2 plus 1 will become 2n plus 3. So everywhere I replaced n by n plus 1. So Pn means I have a sum of the first n terms, but Pn plus first means I have the sum of the first n plus first terms. 1, 4, 9, dot, 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 n squared, and the next one will be n plus 1. Then the right-hand side has to have, instead of n, n plus 1. N plus 1, n plus 1 plus 1. 2 times n plus 1 is 2n plus 2 plus 1 is this. So I assumed that Pn was true. I used it to create n plus first, P of n plus first. And now I will say, fine. If Pn is true, then I can replace all this by what? By what it equals to. I'm going to add n plus first squared. And if I get this, I will say my assumption was correct. If I don't get this, I'll say Pn is wrong. Okay? So I replace this by n plus 1 to n plus 1 divided by 6, and I'm adding n plus 1 squared. If I end up with this, I'll say then my assumption was true, and therefore the sum of I squared is this. So then I will definitely do something here, which is factor out n plus 1. Then I distribute 2n squared plus n divided by 6 and plus 6n plus 6 over 6. Because I only have an n plus 1 that needs a 6. So now I have 2n squared plus 7n plus 6. Do you think that this product at the top will be this? 2n squared plus n squared, 3n squared plus 3n plus 4n plus 6. So I'll write it, of course. So this is n plus 1 multiplied by 2n squared plus 7n plus 6 divided by 6. And I'm so good at factoring because I'll tell you that this is n plus 2 to n plus 3. Of course it is, right? So n times 2n is 2n squared. Positive 3n plus 7 plus 4n is 7n, and 2 times 3 is 6. Since I did get what I was expecting to get, then I will say Pn is indeed true. And then the sum of I squared from I equals 1 through n is indeed n plus 1 to n plus 1 over 6. No one will ask you to prove these. I just want you to see one. You chose one, and that's fine. We can prove all the other two in the same way, using mathematical induction. So now I would like us to pick a linear function. We have 6 minutes. Pick any linear function you want so we can determine the exact area under the graph of that linear function between the 2 points that you want.
46x plus 3.
What about 3x minus 2? Or plus 2, I don't know, it doesn't matter. We just want, I would like to get we can get a negative area. It's possible too. But let's say we want to get a positive area, just to make sure. So this graph looks when x is 0, y is 2. And when y is 0, x is negative 2/3. So yeah, so it's going to be something like this. So now please pick the interval, because we cannot determine the area under the graph without picking an interval.
1 to 4.
1 to 4 is more difficult than 0, so let's do 1 to 4. Good. So first I have the first prep. So we're asked to find the area using the limit of the Riemann sum exactly. Okay. So I need few preps. Delta x is first prep. B minus A over N. B minus A
1 minus 1.
over N. Very good. Number 2. The second prep is xi. Remember the definition for xi. It's A plus I delta x. In this case, it's,
A plus
this is our A and this is our B.
1 plus I delta x.
Yes. 3I over N. Very good. Prep number 3. I have to find f of xi, meaning f of 1 plus 3I over N. What do I write?
3 parentheses 1 plus 3I over n plus 2.
Awesome. So this is 3 plus 9I over N and plus 2, or 9I over N plus 5. Finally, I got to the fourth step. The area equals. And now please tell me what to write. Yes, of course. See why we can't get away from limits? Perfect. Correct, but I would like to put delta x outside. Exactly. That's it. Good. Stay with me, please. We're almost there. So limit as n approaches infinity from 3 over n. And now the summation of a plus b, I, is the summation of a times plus the summation of b, correct? But I also have this, which is a constant, 9 over n, the sum of I from I equals 1 through n. This is a constant, and I only need to apply it, so constant goes in front. Plus 5, the sum of 1 from I equals 1 through n. 5 is 5 times 1. Now, how much is this? N times, right? How much is this? You don't know it by heart yet, but you will. N plus 1 divided by 2. So this is limit as n approaches infinity from 3 over n, 9 over n, n plus 1 over 2, plus 5n. These two go away. The least common denominator is, and also I'll put the n, or let me leave it for now outside. So 2, so this is 9n plus 9 plus 10n. This one needs a 2. Finally, limit as n approaches infinity, 3 multiplied by 19n plus 9 divided by 2n. Knowing limits and knowing L'Hopital's rule, you will give me this answer in a blink.
Wouldn't that 9 go to 18? If you're changing the denominator?
No, because 9 times that. It's not adding.
So 9 and 9 divided by 2. That's okay, that's okay.
I thought the same thing.
So without making any calculations, remembering that the top has the same degree as the bottom as n approaches infinity, or use L'Hopital's rule. What will be the top?
3 times
But it's infinity, so it's infinity.
Infinity.
Okay,
Infinity.
okay, fine, that's fine. Let's do that. So then I have limit as n approaches infinity. So when I differentiate, this is a constant, I get 19 times 3. When I differentiate the bottom, I get 2. I was hoping that you would say, oh, the same degree over same degree is the leading coefficient over the leading coefficient. But that's okay. L'Hopital's rule is fine too. So this is,
57.
yep. And this is exact. Yes, when we will look at a quadratic function, it will be a little bit longer. When we look at a